Hello and welcome to 11th lecture in our comprehensive course on machine learning, artificial intelligence and data science. Now here we want to discuss about this thing called spam filter. Okay. So we are talking about examples of Bayesian theorems application or posterior probability. Okay. The formula is probability of A given a B event has already occurred is equal to probability of B given that A event has already occurred multiplied by probability of A divided by probability of B. Now let us use that. We already discussed this case in the previous example, that is medical diagnosis case. Now we want to discuss the next case. Okay, and that is this. A spam filter will detect spam with 90% of the accuracy. If 10% of the emails are spam, then find the probability that an email is spam given that it was flagged as a spam. So I have copied this sentence because the entire thought process which we did step by step in the previous one, that I want to now just show you as that this is the thought process. Okay, so that is this thing. Now here it is given this thing that a spam filter detects a spam with 90% of the accuracy. I am talking about this case. Okay, so 90% of the accuracy. So what is given to me if I decide from that sentence? Spam filter also is just like something which tests the emails for spam, but it is test, so it detects a spam. So that means what? That the email, if you send 100 spam emails, remember the word 100 spam emails, then it will correctly identify 90 out of 100 as the spam. So that means being spam is already done and it testing positive, that is now occurring with 90% of the probability. So P positive, given that the email is spam, I am writing with mouse, so please pardon me. Okay, given that the email is spam is equal to 0.9, 0.9. Okay, right, and that automatically means testing negative, or rather testing positive when the email is non-spam would be 0.1, 10%, because my this thing classifier, spam classifier, it has 90% accuracy. That means in 10% of the cases it will make error. So even if you give a complete sample of 100 non-spam emails, still it will flag 10% as spam emails. So testing positive when the email sample is of non-spam is 10%, and testing positive when the email sample is entirely of spam is 90%. That is the meaning of 90% accuracy. So I have exhausted this sentence, right? So whatever information I could extract from this sentence, I have exhausted that. Now it is my turn to exhaust this sentence. 10% of the emails are spam. So now that means that nothing is given, the word population is not given, but it is given that it is as a general fact that all over world 10% of the email are spam, like that. Or may not be all over world, but at least for all the emails coming to my company, 10% of the email they are spam. So P spam, that is equal to 0.1. Okay, and that means 90% are non-spam. So that means P non-spam. These are simple probabilities, while these are posterior probabilities. Okay, so P non-spam equals 0.9. Okay, now what you are asked using these 4 parameters, you are asked that find the probability of an email being spam if it was flagged as a spam. So you can say that the testing process gave me that the email is a spam. So it tested as a spam, that event occurred. Okay, but what is the probability that it is actually the spam? Because if my test would be 100% accurate, then there would not be any problem. But my test itself is 90% accurate, and the problem is that out of total population, only 10% of the email are spam. So if an email is spam, then what is the probability? If it is flagged as a spam, so then what is the probability that it is a spam? So that means P positive. That is what you are asked is P spam if it is tested as positively. So that means P spam if the spam testing algorithm tested it positively. Okay, so P spam is if it tested positive in my spam testing algorithm. So just like disease testing is done by some clinical diagnosis, spam testing is done by some algorithm, but that is okay. It is also a kind of test only. So then it is also a kind of statistical test. That is how you should generalize and broaden your idea that events may go on changing, the prediction of disease or the prediction of spam and ham. In next case, there is prediction of manufacturing defects. But fine, that is just domain specific event. But as a whole, when you broaden your concept, then all are nothing but statistical tests. Okay, so then this says that is tested positive as a spam. That is why it was flagged as a spam. But what is its real possibility that it is really a spam? So now I want to find this. So I can use Bayes theorem. Okay, so Bayes theorem says that this P spam positive is equal to P positive spam. That is just interchange the order. Okay, P positive spam. This writing with mouse is a real headache. Actually, I have that tablet, but unfortunately, it's having some issue with this particular PC. Okay, so P positive spam multiplied by P positive divided by P spam. Okay, now if I consider this is Bayes theorem, that P spam positive is equal to P positive spam multiplied by P positive divided by P spam. Now what I am already having, if I see that, then it becomes clear that I am already having this P positive spam. So I can just put that value from here, 0.9, correct? I am also having the value P positive, that is actually I think this only, P maybe positive spam, right? So no, I am having this thing, that is P spam, okay? That is 0.1. So that is this value, and that I am having, and that I can put here, okay? So P spam. I think I have written the Bayes theorem P spam positive. So then it will be, no, why I did interchange that. I should have written here P spam. Sorry, I saw this P spam positive. So then here in the numerator it would be P spam, and in the denominator it would be P positive. Just like previous that medical diagnosis, that type of case. So this P positive, which is in the denominator, that only we want to find. Okay. So for that we need to find it, just like in the previous diagnosis case. So I don't have this, but I have this thing. Okay, so that is, this is here, this will go here, correct? So P positive from a sample of spam. So if I am given a whole sample of 100 spam, then my test will find 90% as positive. So this is 0.9. P spam, out of total population, 10% of the email are spam. So this is 0.1. But P positive is not known to me. So then that P positive can be found in this manner, that P positive is equal to P other two things which are given to me that I can use. So that means P positive non-spam multiplied by P positive spam multiplied by P spam, and P positive non-spam multiplied by P non-spam. So all four terms whichever were given to me, they are used here. Okay. So P positive given that spam, that is this thing 0.90 multiplied by P spam. So mentally you can think that P spam is cancelled, so this is P positive, and similarly P non-spam is cancelled, so this is also P positive. So this is P positive for spam situation, this, and similarly this is P positive for non-spam situation. That is one way of understanding, correct? So then in that case, this all four terms are given to me, so I can easily find P positive. So P positive would be equal to this is 0.9, this multiplied by P spam, simple probability, that is 0.1, then plus P positive non-spam, so that is this multiplied by P non-spam, so that is again 0.9. So it is actually 0.9 multiplied by 0.1 plus 0.1 multiplied by 0.9, or that is 2 times 0.9 multiplied by 0.1, correct? So if I take that value of P positive and substitute it in my equation, then my equation was P spam, given that it is flagged as positive, is equal to 0.90, because this P positive, when whole sample is made up of spam, is accurately detected as spam 90% of the cases. So 0.90 in entire sample, entire population, there are 10% email which are spam. So this is 0.1, and divided by P positive is, I have calculated 2 multiplied by 0.9 multiplied by 0.1, or that means 0.9 and 0.1 they are they are cancelled. So that means what will remain is only the 2 in the denominator, or that means the probability of P spam when something is actually already been flagged as positive is 1 by 2, or that is 0.5, right? So this is what the situation is for something which is for a spam detector. Now you can understand that how difficult it would be for building a very accurate spam detector. You build a spam detector which detects spam with 90% of the accuracy. So that means if entire sample would be of 100 spam messages, then it will correctly identify as 90 of them as the spam. But in spite of them, what is the probability that if an email is spam, given that it was flagged as a spam? So if an email is flagged as a spam by your this classifier filter, then what is the probability that it is actually a spam? Then it is only one half or 50% of the probability. Why it is so difficult? Because this is itself very small number. Only 10% of the emails are spam. So, and that is not in control, because all over world how many emails are spam, that is more or less not in your control. Okay, so this is in your control. Then what you should do is you should try to increase this accuracy as much as possible. And in this case, even that would not make any difference, because by chance this 0.90 and 0.10 and here 0.1 and 0.9. So by chance even that accuracy of detection that gets cancelled. So this will always remain 1/2, irrespective of I can make that 0.95, and of course then this should also be 0.95. So that means 5% of the emails are spam. If 10% remain 10% only, then there is a benefit that I should try to increase this to 95% or 99%. But even that, my effective accuracy, effective probability of something which is being really spam, when my filter flags it as a spam, positive spam, is only around, maybe it would reach around 60% or 70%. So if you can build a spam detector with which works with this posterior probability of maybe 90% or 85%, then you have done a damn good job. Okay, and the reason is not in your algorithm and there whatever scope of improvement, suppose you have already exhausted, but the reason is this is a posterior probability. Okay, and the issue is that only 10% of the emails are spam. So the event itself is rare, and here in that case disease, it was even rare. Only 1% of the population has the disease. Okay, so posterior probability is very, very important and deep concept. So you should now try to do the other 3 examples yourself using this kind of method. Okay, so what I will do in this spam filter, I have given that solution. Similarly, in other also I have given solution, but if you try to do without looking at the solution, here it is given that a factory produces 3% defective products. Now that is actually that population. Okay, that you should understand. So that means that P defective is 3/100 or 0.03, and P non-defective is 97%, or that is 0.97. Now there is a defect detector, so you treat it as a test. In case of disease, it is a clinical test. In case of spam ham, it is a algorithmic test. In case of defect detector, it will be an X-ray or something should be bombarded on the machine part, so that if there are minor cracks, defects, then they will be found out. And that defect detector has 95% accuracy. So that means if 100 defective pieces will be fed to it, then in 95% of the cases, it will correctly identify. So that means probability of test being positive or flagged positive, assuming that the defective is already there, is 0.95. But reverse of that is also true, that if it has 95% accuracy, that means it will have 5% error. So that means that probability of being flagged as positive, even if it is a 100 sample of 100 non-defective products, is still 5%, or that is 0.05. Okay, so by mistake 0.5% of the non-defective product will also be flagged as defective according to this accuracy of 95%. If the defector flags an item as a defective, so the probability, that means the event of flagging as a defective has already been occurred. So in that case, what is the probability that it is actually defective? Okay, so then that is what is asked is probability of being defective given that flag is positive or flagging has already occurred. This is what is asked to you, probability of defective given that flag is already occurred. So what you do is you just interchange the 2 things and write on the RHS is equal to probability of flag given that defective event has occurred multiplied by probability of defective. This term, first term, goes in the numerator and divided by probability of flagging. Okay, so these 2 are absolute probabilities, these 2, while this is relative probability. Now this relative probability is already given to you. Probability of flag as a defective is 95. From a sample of 100 defective products, my test will flag correctly as 95%. Multiplied by probability of defective, that is absolute probability, simple probability, that is in any population 3% are defective products. So that is 0.03. But this probability of flag, that is not given to me. So that you have to find by probability of flag is equal to probability of other, all four terms will be used. Probability of flag being defective multiplied by probability of defective plus probability of flag being non-defective multiplied by probability of non-defective. So always remember that one which is not known, that is always sum of two situations, defective situation and non-defective situation. So from this you find two terms with defective situation and multiply them. So they are this 0.03 and 0.95 here, and find two terms with non-defective situation and multiply them. So that is 0.97 and 0.05. So that is these two terms, and add those two terms, and then that will give me this the 0.07. And if I substitute that in the equation, then I get that 37% of the times whenever a product is flagged as defective, it is actually a defective 37 out of 100 times. So that means my flagging detector had 95% accuracy, but still when it flags a product as defective, it is correct only 37 out of 100 times. Okay, and the reason is not much with its own accuracy, but the reason is that this event itself is quite rare, that it has 3% defective products. Okay, so similarly try this fourth, fifth, and in next lecture we will continue our discussion here. So that will be connecting back to this thing. Okay, that we did actually this probability distribution and data distribution, which are collectively called statistical distribution. And then we suddenly took one detour slightly, and we did permutation combination, and then we did about probability. Okay, what are the uses of or applications of permutation combination, and then we did simple probability and Bayesian probability. Because the reason is that if you talk about probability distribution, then at least you should have some idea about probability. And in any case, without probability, you hardly stand any chance in data science. Okay, recently only I was reading, while just 2 days back I'm recording, I'm recording this lecture, I was reading that Meta in its interview gives a lot of weightage to probability questions. So if you dream to work for some firms like Meta or multinational firm, so in that case you have to be very clear about concepts of probability. Okay, and we are here learning only that much which is important from the point of view of data science. Otherwise, probability in itself is a very deep topic, but fortunately not everything is required in data science. So try to do these other 4 and 5. Solutions are already there. Without looking into the solution, try to do that. And in next time, we will do these various probability distributions. So we see you in the next lecture. Thank you.